Hello, welcome to the NPTEL online certification course on deep learning. In the previous class, we have talked about the linear machines, and we have also started our discussion on multi-class support vector machine. Today's lecture, we will discuss on multi-class support vector machine loss function and also the optimization techniques. So, what we have done in case of linear machine is that we have seen that linear machine is a function that transforms or that maps a d-dimensional feature vector R d into a score function of dimension k. So, score function S that you get is also a vector of dimension k, where k is the number of categories or the number of classes. So, if I expand this, the function looks like this, that f given an input vector x I, f x I w b, where w is the weight matrix and b is the bias vector, is given by w x I plus b, which is equal to the score function s, and we have seen that the score function s has got k number of components, where k is the number of classes or the number of categories. So, given this, we have seen that the score for the jth class or the jth category is the jth component of the score function s, which in this case we have written as sj, and this sj is nothing but wxi, the jth component of this. So, we can write this as f x I w, the jth component. So, the jth component of this gives me the score for the jth class of the ith vector x I, which belongs to class y I. So, these are the training vectors, and because this x I, the input vector, belongs to class y I, so the score function component y I must be maximum. So, when this linear machine gives you the score function, the y I component of the score function must be maximum, because we have taken x I belonging to class y I. And we are not only satisfied with the score function to be maximum, we also want that the score function should be more than the score function of other classes by at least a threshold delta. That means, taken any other class s j, or s of y I, the score function of the class y I, must be greater than s j, where j is any other category other than y I. So, this difference must be greater than some threshold delta. So, accordingly, for the ith component, the loss function that we get L I, which is nothing but maximum of 0 and S j minus S y I plus delta. So, you find that as long as S y I is greater than S j, then it is greater than S j by an amount delta. So, this amount S j minus S y I plus delta will be less than 0. Whereas, if S j is equal to S y I, then this function will be equal to delta, and if S j is greater than S y I, this function will be greater than delta, where delta is a positive threshold. So, in that case, when you take max of 0 and this, output will be this only if it is greater than 0. And the output of this max function will be equal to 0 only when S y I is greater than S j by at least this threshold amount delta. And you sum it over all j not equal to I get the loss component S I. And the overall loss that you get is given by sum of all these loss components. So, to explain this, we had taken an example that suppose I have some x I y I, where this yi is equal to 2, that means this xi belongs to category 2. And suppose the score function that is computed is given by this s equal to 10, 30, minus 20 and 25, and let us assume that we have a threshold delta which is equal to 10. So, if I compute L I, in this case I is equal to 2 because we have taken x I from category 2. So, if I compute L I, you find that it will have these 3 components. One is maximum of 0, 10, minus 30, plus 10, this 10 is delta. The first 10 is the score function for category 1 and 30 is the score function for category 2. So, this is 0, 10 minus 30 plus 10, which becomes minus 30. So, the corresponding max function gives you an output 0. Similarly, for the second case, it is max of minus 20, which is core function for category 3, minus 30, that is core function for category 2, plus 10. Again, this part becomes negative, so output is 0. And for the other one, the score function is 25, which is the score function for category 4. So, it is 25 minus 30 plus 10, and that gives you an output 15. So, as a result, L2 is equal to 15. So, when I compute these score functions, as I said before, that if I take summation of this score function of over all value of I, for all value of j not equal to yi, I get the overall score function. So, this is how we compute the score function, and if you look at the nature of this score function, you find that as long as this component s I s j minus s y I is positive, okay, my score function will be equal to 0 only when this term s j minus s y I, as long as this term is less than delta, my output will be 0. If it is s y I minus s j, this is greater than delta, then output will be equal to 0 because my classification is correct, otherwise the output will be high. So, if I plot this score function with respect to s j minus s y I, the nature of the score function or the plot of the loss function will be something like this, and this loss function is what is known as hinge loss. So, now we have also talked about a term called regularization, because you find that we decide about the classification to be correct or not, or whether we are satisfied with the classification output or not, depending upon the difference s j minus s y I, and which is nothing but w j transpose, that is w j is the jth row of the weight matrix W, that transpose x I minus w y I transpose x I. And if you find that if I scale up this w by a factor lambda, then the score, the difference s j minus s y I will also be scaled up by the same factor lambda. Say for example, for some w, if the difference s j minus s y I is equal to 15, and if I multiply w or scale up w by a factor 2, then the same difference s j minus s y I will be 30. So, there are many possible values of w for which the value of the difference of Sj minus Syi can be greater than delta, right. So, what I need is I need to find out an optimum W or best value of W which will satisfy all my requirement. So, as a result, I have to include a regularization term which is a function of W or the weight matrix, and this regularization term is usually taken to be a L2 norm. So, our regularization term L2 RW becomes lambda times WKL square, where you take the summation of WKL square over all value of K and L. And as a result, our overall loss function becomes L is equal to sum of Li that divided by n, where n is the number of training samples we have, plus lambda times Rw, or the overall loss function in the expanded form is given by this. So, given this overall loss function, now what we need to do is we need to optimize this loss function or minimize this loss function. And in addition to that, what we need to do is we have to also choose the hyperparameters. So, if you look at the previous expression, you find that we have got two hyperparameters over here. One of the hyperparameter is delta, which is the threshold that we have used, and other hyperparameter is lambda, which is in the regularization term. So, if you remember this first term in this loss function, we told this, we defined this as data loss, and the last one is what is known as a regularization loss. So, we have got two hyperparameters over here, one is the threshold delta and other one is this lambda. So, I need to choose that what should be the proper values of these two hyperparameters. However, if you look carefully, you find that both lambda and delta, they control the same trade-off. That is, if the lambda is more, the difference of Sj and Sy will also be more. If lambda is less, the difference of Sj and Syi will also be less. So, accordingly, I will have an effect of lambda. And due to this, we can safely choose the value of lambda is equal to 1. So, that is what we have done over here. The value of lambda is taken to be 1, and accordingly, when you go for minimization of this loss function, the value of lambda will be chosen. So, we have taken value of delta equal to 1, and while do your minimization, accordingly the value of lambda will be chosen. And you find that earlier we have talked about the binary support vector machine, where we have said that given the separating plane between two classes omega 1 and omega 2, during training I will be satisfied only when we find that W transpose Xi for a training vector Xi is more than a normalized distance 1. So, accordingly, a loss function for a binary SVM can be defined like this. It is max of 0 minus Yi W transpose Xi. So, you find that as long as this W transpose Xi is less than 1, that is the normalized distance from W transpose X equal to 0, that is the separating plane, is less than 1, your loss function will be positive. If it is greater than 1, then only loss function will be 0. And the regularization term in case of two class support vector machine, if you remember, we had put this as half of W square. That was the regularization term in case of the two class support vector machine. So, you find that this binary SVM or two class support vector machine is nothing but a special case of a multi-class support vector machine. Right. So, now let us go for how to see how this loss function, what is the nature of this loss function. So, for illustrating this, I consider a 3 class problem, and the sub vectors that I consider is one dimensional vector. So, suppose I have got 3 classes given by the weights W1, W2 and W3, and as I said that I am considering one dimensional vectors. So, each of these W1, W2, W3 are scalars. Okay. And I also take three one dimensional training points, x1 taken from class 1, x2 taken from class 2 and x3 taken from class 3. So, given this situation, you find that the loss functions that we will get is given by L1 is equal to max of 0 and W2 transpose x1. So, this W2 transpose x1 is nothing but score of class 2 for this training vector x1, and this is the score of class 1 for training vector x1. So, the loss function L1 will be max of 0 W2 transpose x1 minus W1 transpose x1 plus 1 plus max of 0 and W3 transpose x1. So, this W3 transpose x1 is the score of class 3 for training vector x1 minus W1 transpose x1 plus 1. Similarly, we define loss function for class 2 L2 for the support vector 2. We also define the loss function L3 for support for the training vector x3, and the overall loss is given by 1/3 of L1 plus L2 plus L3. So, given this, now if we try to visualize how this loss function is, so here you find that in case of L1, if W1 is very small, if this weight vector W1 is very small, then W2 transpose x1 minus W1 transpose x1, this term will be positive, assuming that W1 transpose x1 is less than W2 transpose x1. So, output loss function will be positive, which is max of 0 and this. And this particular term will be 0 only when W1 transpose x1 is more than W2 transpose x1 at least by 1. That means, as long as W1 is very small, your loss function given by this value of loss is positive. Similarly, in this case, as long as W1 is less than W3, here also it will be positive. However, as W1 goes on increasing, the loss function gradually reduces and ultimately it becomes 0 and remains 0 for this component L1. Similarly, for component L2, you find that when W1 is very small compared to this, so that this term becomes negative, the output will be 0. And as W1 goes on increasing, eventually this term becomes positive, so output L1 will also become positive and it will have a certain value, it is not 0, and same is for L3. So, by this understanding, having this understanding, now we can try to plot the different loss functions L1, L2 and L3. So, if I plot L1 with W1, you find that, as we said, that when W1 is very small, the loss component L1 is positive and it goes on reducing as value of W1 increases. Similarly, the other component L2, initially it remains 0 with respect to W1, initially it remains 0, and when W1 becomes very high, in the sense that W1 x1 becomes more than W2 x2 by a factor 1, by the threshold 1, then the loss function becomes positive and it is like this. And same is the case with component L3. And my overall loss function is average of all these three components L1, L2 and L3, and the overall loss function is given by this. So, by looking at this figure on the right, which gives you the overall loss function, you find that the loss function is convex, right. So, this can be solved using convex optimization problems, because the loss function that you get is convex. Now, here the situation is very simple. We can visualize it very easily because I am considering W1 to be a scalar or a one-dimensional vector. Now, what happens in case of multiple dimensions? Usually, our weight vectors or the sample vectors, they are of very large dimension, maybe of the order of thousands. So, the visualization of the loss function in such cases is very difficult. However, we can try to visualize that section wise. So, what I do is, now I know that my loss function is defined in a high dimensional space. So, I can take a single point in that high dimensional space at random, which is a W, and I take a direction W1 which is also at random. So, this W1 I take as a direction passing through the selected point W. And as we move along the direction of W1, you go on recording the loss function. Or effectively, what you do is, every point in the direction of W1 passing through W is represented by this expression W plus A times W1, where A indicates that what is the position of the point on the line W1 passing through W. And we are taking the loss function L at those different points. By varying A, I get different points, and you take the loss function W at all those different points. So, what I can do is, I can now plot the loss function as a function of A, or as A varies, I get different points on the line, and now if I record the loss functions, I get a loss function which is of this form, which is LW plus AW1. A is the parameter which determines the points on line W1 in the direction of W1 passing through W, and you find that the loss function which will be of this form. I can also try to define loss function on a plane if I take the section on a plane. So, in that case, what I have to do is, instead of taking just W1 a single line, I have to take W1 and W2 as two different lines. Okay? And by giving that, every point on that plane defined by these two directions W1 and W2 now can be determined by this expression W plus A times W1 plus B times W2. And again, if I record the loss value for different values of A and B, which are the parameters in this particular case, I get a loss function which is given in this form. So, this is the plot of the loss function in two dimension. So, in both the cases, whether I take the previous one like this, where you find that again the loss function is a convex function, it has a minimum somewhere over here, or I take the next one, that is visualization of the loss function in a plane, you find that here again the loss function is a convex one, where the blue, that is in this particular case at the center, here it is minimum, and the red represents maximum loss function. So, I have the minimum of loss over here. So, the loss function in two dimension again shows that it is a convex one. And this is the plot that I get if I consider, or if I plot the loss function only for a single sample or a single vector, training vector. And when I average this over multiple number of training vectors, the loss function becomes something like this. So, you find that this averaging over all the training samples smooths the nature of the loss function. So, once I have this loss function, next what I need to do is, I have to optimize this loss function, or I have to minimize the loss function. So, for minimization, as we have done earlier, we take the gradient descent approach. So, I have to take the gradient of the loss function that I have, and I modify W in the direction of the negative gradient. So, here what I have is, as we have already said, that the overall loss function is given by this, where this is the data loss component and this is the regularization loss component. If I take, so I have to optimize this loss function in order to find out the value of W for which this loss function will be minimum. So, I take the gradient of this loss function with respect to Wi. I also take the gradient of this loss function with respect to Wj. So, when you take the gradient of this loss function with respect to Wi, you find that the expression of the gradient will be that it is sum of xi, that is gradient of loss function with respect to Wi is nothing but sum of xi only in those cases where Wj transpose xi minus Wi transpose xi plus delta is greater than 0. And because in all the cases where J transpose xi minus Wi transpose xi plus delta is less than 0, the loss function was 0. So, for those cases, those xi's are correctly classified by our W. So, in such cases, I need not modify the weight matrix W. So, this gradient only takes the sum of all those xi, all those training vector for which Wj transpose xi minus Wi transpose xi plus delta is greater than 0. That means, these are that xi leads to an error. Plus, if you take the gradient of this term, this gradient will be actually twice lambda times Wi. So, in this case, it is written with respect to another constant, say eta times Wi. In the same manner, if you take the gradient with respect to Wj, then it also becomes sum of yi, where Wj transpose xi minus Wi transpose xi plus delta is greater than 0. So, we will take the sum of only those training vectors for which this condition is true. We will not consider those training vectors for which this condition is not true. That means, those training vectors are correctly classified for the by the current W. And plus, from this regularization term, when you take the derivative of this regularization term with respect to Wj, or take the gradient of this regularization term with respect to Wj, the term that I get is zeta times Wj. So, these are the gradients, and using these gradients we go for our optimization step or gradient descent step, where we get the gradient descent as at the kth instant, if my weight vector was Wik, then the next iterated value of Wi is becomes Wik plus 1, which is 1 minus eta times Wik plus 1 over n sum of xi for all those xi which satisfies this condition. Similarly, the iterated value of Wj at instant k plus 1 from instant k, from the iterative step k, is given by Wj k plus 1 is equal to 1 minus zeta times Wjk minus 1 over n sum of all those xi for which this condition is satisfied. So, we will not consider those sample vectors which does not satisfy this condition, because we assume that those vectors are correctly classified by the Wj at the kth instant. Okay. So, if you look at these two gradient descent steps, you find that what it indicates is, first you are modifying Wi which was there at the kth instant by the regularization term. So, this is a component which is coming from the regularization error part or regularization loss part, and this is the component which comes from your data loss part. So, that is how iteratively you go on optimizing or minimizing this loss function, and when it converges, the value of weight matrix that you get gives you the linear machine or the support vector machine for multiple classes. So, we will stop here today's lecture. We will come back in the next day. Thank you.